we present rapid iron-on user interfaces, a new prototyping principle for E-Textiles. Current E-Textile prototyping approaches are commonly quite time-consuming. Automating these processes would require machinery typically outside the realm of a prototyping space. We see a promising potential in ultra-thin and functional fabrics as well as printed electronics. Inspired by the simplicity and versatility of correction and packaging tapes, our approach transfers these techniques for E-Textile prototyping. For that, we propose to combine ironing and dispenser techniques. With rapid iron-on, we present a new prototyping principle for E-Textiles that allows to physically sketch user interfaces in a hands-on manner directly on textiles. Our approach builds on functional textile tapes and patches, which comprise heat-activated adhesive to be easily ironed onto fabrics. Example applications. The example of a smart white code demonstrates how iron-on enhancements can help to get access to secured areas or pager notifications. Our interactive bag integrates smart functions including interior lights that illuminate when the bag is open, moisture sensors at the bag's bottom, and capacitive buttons and sliders for controlling a music player. We build a tool with two wheel axles that can hold spools. By pushing the device down, a spring-loaded iron transfers the tape. A small actuated blade cuts the tape. Furthermore, custom arrangements of tapes are possible to iron multiple tapes at once. Traces are ironed on by pressing down and moving the device. Connecting traces is possible by placing and ironing a special patch with a slit. Some metal zippers only have conductive connections between opposite teeth. For instance, this could be useful for microcontroller patches that can be easily detached. For bridging traces, an isolation patch can be placed. Components can be peeled off by ironing the parts again. Our techniques do not only allow for creating electronic circuits, in addition they can be used to realize sensors of custom shape that are embedded on a textile. For that, the designer sketches traces, applies a layer of piezo-resistive fabric, and finally another layer of traces, to create a multiplexed force matrix sensor. In the following, we introduce a library of components that demonstrates the versatility of our approach. Input components. As an example, we introduce capacitive electrode patches that make cuff buttons interactive. Therefore, the designer first places the patch, then uses the rapid iron-on tool in ironing mode. Peels of the carrier and protection layer of the patch. Connects all traces by using a 4-wire tape. Tests the sensor with a metal button, and finally covers the sensor with elastic fabric, and places a button to finish the elastic cuff button control. Furthermore, we enhance ultra-thin NFC tags with iron-on adhesive. This allows a designer to just place a tag and iron it onto the textile. After peeling off the patch carrier, the tag is strongly connected to the fabric. If the designer turns the clothing, the NFC tag is not visible anymore. NFC tags could be read or written to from any NFC device. Output modules. We use bendable e-ink displays to fabricate patches that can be ironed and connected with a multi-wire tape. Wiring components. To support elastic traces, we contribute traces that are stretchable by using a horseshoe pattern. Breakout patches are useful for attaching some special components, like lily pad microcontrollers. Computing components. By using our U-shape iron, it is further possible to iron on semi-flex electronics. Following, we will explain how we made iron-on tapes and patches. First, we iron on fusible inner linings to prepare the material. Afterwards, we cut the material using a laser or vinyl cutter. A carrier layer with sticky glue helps us to transfer the functional material true to scale to tapes and patches. Finally, the material has to be rolled onto a spool, making the tape ready for the rapid iron-on device. More complex traces, like shielded ones consisting of multiple layers, can also be fabricated in a similar manner. For that, all functional layers are ironed together, and the final tape is again rolled on a spool. The technical realization of the rapid iron-on device includes 3D printed parts, a modified soldering iron, 2 timing belts, a small blade, and exchangeable spools and metal axles. Detailed building instructions are available on our website. In summary, we contribute a new technique for rapid fabrication of E-Textiles, the realization of a handheld ironing tool, a comprehensive library of components, 3 implemented example applications, and technical experiments and 3 expert reviews.